Okay, hello everyone. Welcome back to the Topos Institute Colloquium. Today we're very happy to have Marcelo Aguiar talking to us about the Eckmann-Hilton argument in duoidal categories. So please, Marcelo, whenever you're ready.
Thank you, David. Yes, so I'll go right ahead, but you should know that I'm happy to answer questions at any point or comments that you want to make. You don't need to wait until the end. I don't see comments in the chat though, so David, if you can help me with that, that would
Yes,
be
I'll read
great.
them to you if they come up.
Excellent. All right. So what I'll tell you about mainly is an introduction to duoidal categories. Hopefully that's useful for some of you at least. There is an application at the end we may get to if we have time. If we don't, the slides will be available and there will be things there to complement what I managed to say during the talk. Most of this work is coming from earlier work with Swapneel Mahajan on the foundations of duoidal categories, and some more recent work with Javier Coppola, in which we derive a particular application to Hochschild cohomology, and that's what we'll enter at the very end. Okay, so let's go ahead with the definition of duoidal category. So one point of departure that we may take is here at the Eckmann-Hilton argument. So this is formulated in this manner. It's a basic fact in abstract algebra. We have a set with two operations that satisfy these axioms. Each one has a unit element, and there is this axiom linking the two that you see up here. And whenever you're dealing with such an object, one set with two operations satisfying these axioms, then it follows that the operations coincide. They also share the unit elements coincide, and the operation is both commutative and associative. All of that follows from those simple axioms. This is a simple exercise that one can do in an introductory algebra course. It is called the Eckmann-Hilton argument because it appeared embedded in the proof of the commutativity of the higher homotopy groups by Eckmann and Hilton. So today we refer to it as the Eckmann-Hilton argument. All right, we're going to come back to this in various ways throughout the talk. So this is really, even though it's basic, it's very important as well. So if we adopt this pictorial notation for the Eckmann-Hilton axiom, that axiom linking the two operations that we had on the previous slide, vaguely represented by this diagram in which we mean, on the left, this picture represents that you first operate, let's say, across, whereas on the other side, we first operate vertically. Then the Eckmann-Hilton argument is the equality between two such ways of operating. So first across, then vertically, or first vertically, then horizontally. If we view the Eckmann-Hilton axiom in that manner, then we may say that a duoidal category is a context in which we replace the set by a category, the two operations by two monoidal structures on the category, and the axiom linking the two operations by a natural transformation, coherent maps, a natural transformation subject to some coherent conditions between these two objects. So again, this now, before little a, b, c, and d represented elements of the set, now capital A, B, C, and D represent objects of a category. And these two diagrams represent the two different ways of operating in order with these four objects. We're going to make this more precise in a second, but that is the basic idea. So, all right. So here's what I said in a little more detail. So a duoidal structure on a category C consists of two monoidal structures. So two monoidal, two functors that we call tensor products. And I'm going to use this unusual notation of diamond and star for each of the two monoidal operations. Each one has its unit object. We're going to use J and K for them. And then there is this natural transformation connecting these two fourfold products among the four objects that we refer to as the interchange law of our duoidal category. There's also three morphisms involving unit objects. As indicated there, we won't need all of this detail, but that's all the ingredients that intervene in the definition of a duoidal category. So the complete definition appeared in work of Richard Garner and myself with Swapneel Mahajan, more or less at the same time and independently. But of course, there were presents in the literature. We'll see that this is not it's a simple notion to understand. There were presents in work of Altiano and Fyodorovich, but their definition was a bit restrictive. It wasn't the full definition that we need to encompass most of the examples, okay? Their definition would leave out many examples that we want to work with. Their definition basically amounted to our definition in which you further impose the condition that the unit objects J and K coincide, and then a lot of the structure simplifies or disappears. But we don't want to do that, okay? So another look at the interchange law. This is what I was anticipating before, that it is a map of this kind. We may represent it pictorially in this manner. I won't insist with those pictures anymore. Important fact, the interchange law is not required to be invertible. It is a natural transformation, but not a natural isomorphism. And another observation is that the order in which we list the operations, the two monoidal structures of our category, matters. Because if you look at the way the interchange law maps, it certainly doesn't map the other way around. So if you switch the order of diamond and star in a duoidal category, you may not obtain another duoidal category because you may not have another interchange law mapping in the opposite direction. Okay, so when we speak of a duoidal category, we have to specify the order of the two monoidal operations and also the interchange law that should go along with that. All right, now a precise look at the axioms. What are the axioms that I haven't yet discussed? This is all you need to remember for the rest of the talk, that the second monoidal structure should be monoidal with respect to the first when viewed as a functor from C cross C to C. And the first monoidal structure should be comonoidal with respect to the first. So here, monoidal and comonoidal refer to the two kinds of monoidal functors that we may have between monoidal categories. Sometimes they're called lax monoidal and co-lax monoidal. We're using here this abbreviation of monoidal and comonoidal. So I'm assuming that we are familiar with that. We'll come back to functors later, but for now, let's just say that that's the definition. Again, if we want to look at it more closely, there is this slide. I'll let you read it later. It just says a little more slowly what I tried to summarize before about how to view. So there's one important point to make here. It is that when we say that each monoidal structure is either monoidal or comonoidal with respect to the other, the structure maps that intervenes in those two monoidal and comonoidal functors is always the same interchange law zeta. Okay, so I'll let you read this later. To make this more concrete still, this is what this amounts to in the end when you unpack it and turn it into commutative diagrams. These are the two main axioms. There are other axioms involving the unit objects, but as far as associativity is concerned, these are the two axioms. Notice that the associativity of both monoidal structures is omitted here. I'm writing the axioms as if the two monoidal categories, the two monoidal structures on our category were strict. This is not an assumption, but it is for purposes of this talk that the axioms are drawn in this manner. So basically, the interchange law involves two objects constructed out of 4, A, B, C, and D. And here we have 6 objects coming in, and they can be grouped either in 3 pairs or into triples. And that's how these axioms come about. All right, so it's just a quick look at the definition of duoidal categories. Return to examples. Possibly the first class of examples that we want to address is this one. Every time you have a braided monoidal category, you also have a duoidal category in which you use the given monoidal structure twice. You repeat the monoidal structure, you duplicate it, so you let diamond and star be the same given monoidal structure on your braided monoidal category, and you use the braiding to define the interchange law. In this case, so remember, again, if I go back, that the interchange law maps as indicated here. When the two monoidal operations are the same, then we are in this situation. The domain and the codomain of the interchange law simply differ in the order of the middle factors. So if we have a braiding available, then we can use it to define the interchange law. And the axioms hold. The braiding axioms imply the axioms for a duoidal category.
And vice versa. Is that right?
Yes.
And vice
Sorry?
versa. And vice versa. If you had the same monoidal operation and it was duoidal, you would have a braiding. So both directions.
So the answer is yes. In this is stated here at the bottom of the slide in this proposition. But notice importantly that for the answer to be yes, you need to know, in addition, that all the structure maps of your duoidal category are invertible. If not, the converse doesn't hold. So in fact, we have an example of a duoidal category in which the two monoidal operations coincide, the two monoidal structures coincide, but the interchange law is not constructed in this manner from a braiding or even from a lax braiding. Okay, the interchange law is more complicated. That is possible. It is not possible, though, if you require the interchange law and all the unit maps to be invertible. And that result, we can say, goes back to Schoyal and Street in their original paper on braided monoidal categories. You won't find the language duoidal categories in there. They hadn't been defined, but what they are considering in effect is a duoidal category in which all the structure maps are invertible. So that result is in their paper. So this is a categorical version of the Eckmann-Hilton argument. So again, the Eckmann-Hilton argument is surfacing here, but it'll reappear later in the talk in other ways. Okay, so all right. So what do we have so far? The notion of duoidal categories and one class of examples, the one provided by braided monoidal categories. We should see examples that are not of this kind, in which the two monoidal operations are distinct. Well, here's possibly the simplest one of that nature, or one of those. You fix a monoid, an ordinary monoid in sets, and let's say we work over a commutative ring K. K will always be a commutative ring in the talk. And then we look at the category of m-graded K modules. So tuples of K modules in which each component, tuples in which each component is a K module, and the tuple is indexed by elements of M, capital M. This category is duoidal. There are two natural monoidal structures on this category. One is this type of Cauchy product in which you form this convolution, this direct sum over all ways of decomposing an element little m, and that defines the component of degree little m in the diamond product of x and y. For the star product of x and y, you want to define the n component, and you just take this diagonal product. Both make sense. Both give rise to a monoidal structure in the category C of m-graded K modules, and they are compatible. There is an interchange law that one can define. I'm not stopping here to show you how to define it or how it is defined, but it is a natural inclusion that exists from one side from the domain of the interchange law to the codomain of the interchange law. There is a natural inclusion. When you sit down and write it out, you see that one side sits naturally in the other. And the unit objects are different. That's what they are, J and K. I'm describing the components of J and K. All right, so that's one example. So here's another example, the category of spans over a set X. So X is fixed, and you look at spans. So the objects are triples. So X is fixed. What's varying here is the head of the span, let's call it A, and the legs, S and T. We use this representation for the elements of A. Little a is an element of A, as always. S of A is the source of the arrow A, T of A is the target. That's how we can picture an element of A together with the maps S and T. And then there are two ways of multiplying spans. We can either take these pairs of arrows in which the source of one is the target of the other, composable arrows, arrows in series, as shown here on the left, or we can take pairs in which that have the same source, in which the elements of the pair have the same source and the same target, so arrows in parallel. And again, these two operations, each of them defines a monoidal structure on the category, and they are compatible. There is an interchange law, again, defined naturally as an inclusion. All Of course, this construction can be carried out more generally in the category of spans over an object in any category with pullbacks and a terminal object. But for us, this example will suffice. In fact, it won't be essential. I want to go quickly over the examples. I'm assuming that the audience here is very familiar with categories, and perhaps everything I'm saying is overly straightforward. So I'm trying to rush to the end where perhaps the new considerations will appear. Here's another family of examples. Start from an arbitrary monoidal category. So you have one monoidal structure, okay? But suppose that C also has finite products, all finite products. So binary products and a terminal object. Then you can view C as a Cartesian monoidal category, right? You can use products to define a monoidal structure on C. So at that point, you have two monoidal structures on C. The one given by products, the Cartesian structure, and the original one, that in principle have nothing to do with each other. However, there is always an interchange law. You can always turn such a category C into a duoidal category because there is a canonical map from this object that I am pointing to with my mouse here to that object. Oh, that diamond should be a tensor. That's a typo. It is the map defined by the universal property of the product with this component. So basically what you do is from here, you can map to a tensor C simply by projecting, right? You can project this factor to A and you can project this factor to C. And then you end up with a map to a tensor C. Similarly, you can project to the rightmost factors and you have this map that goes to B tensor D. So the universal property then gives you this map and it satisfies the axioms. So one has another family of examples. The category of spans that we saw before is of this form because the second structure that we had on the previous slide is the categorical product on the category of spans over X. So this is of this kind. So another large family of examples. Now, what about this one? Well, quickly, I think we want to view it quickly. You fix a commutative algebra, R, and then you look at R by modules. Since R is commutative, R by modules are the same thing as R tensor R modules, right? Otherwise, I will have to say R tensor R op, but I want R to be commutative for a reason that perhaps we can discuss in a second. So in that category of R by modules, there are two monoidal structures. First, you can tensor by modules over R using the right module structure of X and the left module structure of Y. That gives rise to the star operation. This is naturally an R by module because I have the left module structure of X and the right module structure of Y to still operate on. Now, another thing you can do is to tensor over R tensor R, because R tensor R is commutative, so this tensor product is defined. X is both a left and a right R tensor R module, same thing for Y. So I can tensor and I can turn this object again into an R tensor R module. This is where I use that R is commutative. This is what wouldn't work if I attempted to do this in the non-commutative case and I were looking at this category as the category of R tensor R op modules. I wouldn't have this operation at my disposal. So when you do this, everything works. You have an interchange law. It is here, it is briefly described how it is defined. It is inherited, it is constructed from the usual braiding or symmetry on the category of little k modules. So at that level, you can just switch the middle factors. But down here, when you go down, so each of these objects are quotients, right, of the tensor product over little k. So you have these quotient maps, and then it turns out that this map factors to the quotient, giving rise to the interchange law. So this is another source of examples in which the interchange law, or in which we have two honestly distinct monoidal operations, and the interchange law then is not a braiding, it's not constructed from a braiding, but it is still in some way of that flavor in the sense that it is coming from a braiding upstairs. Hopefully that was not too confusing. It is just a side example that won't be central to our talk, but I want to have it in. All right, so what do we want to do? We want to consider algebraic structures in duoidal categories. In monoidal categories, categories with one monoidal operation, well, we can consider monoids, comonoids. And if the monoidal operation is braided, we can consider bimonoids. Well, what about duoidal categories? Well, this is what we can do. Everything is based on this simple observation. If you have a duoidal category and you look at monoids with respect to the first operation, the one that I am denoting by diamond, that category inherits the second operation. So you can take the star product of two diamond monoids and I get another diamond monoid. So you have this new monoidal category, the category of monoids, the category of diamond monoids. And similarly, you have this other monoidal category of star comonoids. This one inherits the first monoidal operation, the star operation. So this category is monoidal under diamond. And in addition, one can check very quickly that if you look at comonoids in this category, necessarily with respect to star, and monoids in this category, necessarily with respect to diamond, then those two notions coincide. There is an equivalence between those two categories. All right, so this gives rise to these three definitions. We can speak of bimonoids in a duoidal category as in this manner, as either comonoids in the category of monoids or monoids in the category of comonoids, as indicated here. But you can also look at duoids and coduoids. What are they? Well, duoids are monoids in this category. So monoids with respect to star in the category of monoids with respect to diamond. Those are duoids. And similarly, or dually, you have the notion of coduoids. All right, so here's the diagram. The only thing you have to keep in mind, if you have a duoidal category C, well, you can look at monoids and comonoids. This you can do for any monoidal category. So here I'm looking at monoids with respect to diamond, and over here, comonoids with respect to star. And then you can iterate this and obtain these three new categories. So are there any questions here? Is this okay? This is just the familiar fact about braided monoidal categories that we can define bimonoids in braided monoidal categories extended to duoidal categories, which we've seen are more general than duoidal categories. Together with the addition of these two categories, which we normally do not consider in the setting of braided monoidal categories for a reason that you might suspect and that we will discuss in a second. So if everything is okay, I continue. All right, so what I'm going to do now is take a quick look at bimonoids and then at duoids in more concrete detail. So because the definition we gave before is packed, let's unpack it. So what is a bimonoid in a duoidal category C? Well, it is an object. It has a multiplication with respect to diamond and a co-multiplication with respect to star because of the way we defined it. And the compatibility axiom, the main compatibility axiom boils down to this. So this is just the familiar axiom for a bimonoid. Usually, in the usual axiom, you will have here identity, tensor the braiding, tensor identity. That gets replaced by the interchange law in this setting, in this more general setting. Otherwise, this is the usual axiom. And of course, this can be read in two equivalent ways by saying that mu is a morphism of comonoids or delta is a morphism of monoids. Of course, for those assertions, you always have to be careful about what operation you are referring to, what monoidal operation you are referring to. All right, so those are bimonoids. What about examples? Well, if we specialize this definition to the case of braided monoidal categories, we get the usual notion of bimonoid. So for example, in vector spaces, under the usual tensor product, we get the usual notion of bialgebra, and so on. In these type of examples in which we had the second operation was Cartesian, well, comonoids in that setting, every object has a unique comonoid structure, and as a consequence, then every monoid has a unique bimonoid structure. So that's all we get for those examples. In particular, this applies to the category of spans, which was of this form. So what does that mean? Well, a bimonoid in spans is simply a category with object set X. And it's the same thing as a monoid in spans. So we don't get anything new in that setting. On the other hand, if you go a little bit further and you replace spans for objects that are bigraded, so K modules that are because a span, after all, is a set that is bigraded over X, right? You have the two maps S and T, which give you the two gradings. Well, you can do the same thing with K modules. Suppose you have K modules bigraded over X. The same game can be played. You get a duoidal category, and you can look at bimonoids there, and they happen to be exactly what these authors defined directly and named in this manner as semi-Hoff categories. So why semi is because if you go beyond bimonoids to Hoff monoids, then you can speak also of Hoff categories, but we won't be doing that in this talk. What about bimonoids in the category of M-graded modules? The one where we had those two operations, one which was a Cauchy, was defined by a convolution formula as a Cauchy product, and the other one as a Hadamard product diagonally. Well, again, those objects were defined, have appeared in the literature without reference to the general setting of the duoidal categories. So they appeared in work of Turayev. And such an object looks like this, all right? So you have a graded module with maps of this kind in which the multiplication adds up the degrees, mixes up the degrees. The commultiplication simply is internal to each component. All right, and finally, what is a bimonoid in the category of R bimodules? So I'm going a little bit quickly, so perhaps it's unclear what category I'm referring to when I speak of R bimodules. I'm talking about that last one that we discussed. Is it still here? This one here. A bimonoid there is precisely a bialgebroid, another classical notion, bialgebroid with commutative base R. The notion of bialgebroid can be defined in the non-commutative case, but it is more complicated and cannot be captured in these simple terms. There is work of Gabriela Bohm in that direction, and also other authors, but again, I'm not going there in this talk. So that's it for examples of bimonoids. I want to turn to duoids. So these objects are a little more mysterious, and they're really the focus of our talk. I want to tell you that duoids have a right to exist, and they can be interesting and useful for something. So let's see if we can move in that direction. So a duoid, remember, a duoid was defined as a monoid in monoids. So it is an object with two operations then. One with respect to diamond, one with respect to star. It should be a monoid with respect to each. And then you have the compatibility axiom that relates the two multiplications. And this is what it is. Very similar to the compatibility axiom for a bimonoid. In that axiom, you had this arrow going up, involving the two commultiplications. That arrow got switched, and this is what it looks like. Here you still have the interchange law. Well, and the other arrow that goes switched is here. Here you have the commultiplication going the other way. This axiom can be read in one way, not in two ways as for the case of bimonoids, in one way. All this says is that nu is a morphism of diamond monoids, because you can view all this composite across the top right of the diagram as the multiplication on D star D. Okay, the monoid structure or the monoid operation on D star D. So that's what a duoid is. And of course, we have the dual notion of coduoid. Now, let's see if there are examples of duoids. Well, first, for the case that explains why we normally don't consider this notion in the special case of braided monoidal categories. It is because we have the Eckmann-Hilton argument at this level. This is a simple fact that one can check. I guess this comes from my work with Mahajan, but it is, well, it does require a proof, but it is simple. This is what it says. If you have a braided monoidal category and you consider a duoid in the associated duoidal category, remember, in which you duplicate the monoidal structure, you put it twice, and you use the braiding to define the interchange law. You can consider duoids there. What are they? Well, the structure collapses. It happens that the two monoid structures coincide and they are commutative. So a duoid in a braided monoidal category is nothing but a commutative monoid. This is, of course, the well, I forget now how John Baez calls this, but it is that simple idea that you all know well. Anyway, so yeah, so I shouldn't say that this comes from my work with Mahajan, because without the language of duoidal categories, this is a well-known fact. Okay. All right. So that's that. And of course, this generalizes the classical Eckmann-Hilton argument, which is the special case in which C is the category of sets under Cartesian product. Now, I want to consider this question. Might this hold in some form in more general duoidal categories? So what can we say about duoids in more general duoidal categories? Now, at first, one sees that the answer is no. I mean, there isn't anything you can say in general because, or at least of this kind, because in this general setting of duoidal categories, the two monoidal operations, let me go back, have a different domain. The two monoidal, the two multiplications have different domains, D diamond D and D star D, so they cannot coincide, which is the conclusion of Eckmann-Hilton. So this question looks a little bit funny. However, we'll see that there is something one can say, very interestingly. It won't hold in the general setting of duoidal categories, but in a special setting, yet more general than the setting of braided monoidal categories, there is such a result. And we'll discuss that in a second. On this slide, I have some examples of duoids. I'll let people read the second example later. Let me just spend a second reading the first example. In the category of spans, remember we discussed what a monoid was? We discussed what a bimonoid was, and that was a category, and we said that there was also a monoid with respect to the first operation. So a duoid should be something more special than a category, because a duoid is in particular a monoid with respect to the first operation. So it should be a category with object set X plus something else. And the plus is simply this. It is a category enriched over the category of monoid, in the category of monoids. So that's a nice example in which we can understand what a duoid is. And you see that in that case, there is no collapse of structure. Okay, a duoid has a right to exist. It is that, and it is nothing else. The second example, I'm skipping. It is there just to tell you that there are examples that are not trivial. Now here I have a few slides that again I'm going to skip, but I'm just going to tell you that what I call the most famous coduoid, this is an example of a coduoid, is the two-sphere. The two-sphere has, in an appropriate category, has a structure of coduoid. And maybe just look at these pictures. So the square represents S2 with the base of the square identified, sorry, yes, with the base of the square identified to a point. So the square becomes a two-sphere. And there are two maps, delta 1 and delta 2, and they give rise to the two comultiplications of a coduoid on the sphere. And this example is, again, something that one can say is implicit in the original Eckmann-Hilton argument. This is the other half of the proof. There is the first one half is what I had on the first slide, this set theoretic or algebraic fact. And the other half one can read in this slide, in these terms. When you put the two together, one obtains the fact that the second homotopy group is commutative because it is a convolution monoid from a co-commutative comonoid to a commutative monoid. And right, so where does Eckmann-Hilton enter here? So what happens is that S2 is naturally a coduoid. This is what you see. You don't see the co-commutativity, but you do see the axiom for a coduoid. And because you can apply Eckmann-Hilton, because we're dealing in this case with a braided monoidal category, our duoidal category is a braided monoidal category, you can conclude that the coduoid is in fact a co-commutative comonoid. And that's the key for deducing the commutativity of the second homotopy group. I'm skipping this, okay? Again, this is just an announcement, perhaps. Hopefully it made sense. And if you want more details, you can look at those slides later. Normal duoidal categories. So we're going to introduce a class of duoidal categories that sits between braided monoidal categories and the general duoidal categories. These are the normal duoidal categories. And this definition comes from work of Richard Garner and Ignacio López-Franco. So in any duoidal category, you can build this map. So you can wonder whether you can relate one of the products to the other using the structural maps of a duoidal category. And this is something you can do. If you start from the diamond of two objects and you insert the unit object for the other operation, star. So because K is the unit object for star, you have a natural isomorphism here. And now you can use zeta, and you end up here. Well, K was the unit object for star, not for diamond. So there's nothing else you can do. So you don't land where you would want, which is X diamond, X star Y, but you end somewhere close. There is a similar thing you can do if the insertion of the unit object is on the extremes rather than in the middle. So as you see here, you insert K at either end. Again, you have an isomorphism, and then you middle interchange, you use the interchange law, and you end up there. Now, what would happen if you were to do this for a braided monoidal category in which the two operations are the same? Well, in that case, the two operations are the same, and the unit object is the same, so you're going from X tensor Y to X tensor Y by means of sigma. And by means of tau, you're going from X tensor Y to Y tensor X. And in fact, what you recover, if you look back at what zeta was in this case, are the identity and the braiding. The fact that this is the identity, in this case, is the first result that Schweial and Street prove in their paper on braided monoidal categories. That when you braid the unit object with itself, that's always the identity as a consequence of the axioms. All right, but we really want to be doing this not in the case of braided monoidal categories, but in the case of normal duoidal categories. So what are those? Those are categories in which the unit objects coincide. So this will be the categories of Baltiano and Fyodorovich. So they are important for us as well. All right, so in this case, these transformations that we introduce, sigma and tau, map as indicated here. So things simplify and look nicer. And we should think that sigma is a generalization of the identity, and tau is a generalization of the braiding. That's what they would be if we were in the setting of braided monoidal categories. All right, so are there examples of normal duoidal categories? Yes, any braided monoidal category, and here quickly, just to give you one, similar to the category of topological spaces that I skipped over before, the category of pointed sets, and the product and coproduct. The coproduct is the wedge at the base, and the product is just Cartesian product. And the common unit object is a singleton. That's an example of a normal duoidal category. Okay, but let's leave those examples aside. This is one main example that, if we have time at the end, will play a central role, the category of cosimplicial modules. So I don't have time to remind you of what a cosimplicial module is, but it is dual to the notion of a simplicial module. And it's important that I'm working in a linear setting because I want to perform this construction that involves a quotient involving linear relations, okay? Now, in the category of cosimplicial objects, there's always this operation, the diagonal product. This doesn't require the linear structure. This is the usual structure on cosimplicial, or even simplicial, we would do the same. But on the category of cosimplicial modules, there is another monoidal structure that we found with my co-author Coppola, and then we discovered that it had been introduced by Batanin for purposes separate from ours. But it happens that, so Batanin defined this structure, but he didn't consider what would happen if you put these two structures together. The usual one here, and this other one, X diamond Y. It happens that you obtain a duoidal category. Moreover, the category is normal, and the unit object, the common unit object, is the constant cosimplicial module. So what are we doing here in this construction? So you see, you start by forming a convolution product as we did for graded modules. After all, a cosimplicial object is graded over the natural numbers. So that's what I'm doing here. But if you do just that, you cannot turn this into another cosimplicial object. We have too many cofaces. And what you do is you co-equalize the last coface of x with the first coface of y. So don't worry too much about the indices and the details, but that's morally what's happening here. And that does the trick. So that's that monoid structure. And the nice thing is that it is compatible with the other one, and one gets a duoidal structure. All right, so let's go back to the general theory. Normal duoidal categories. What happens to duoids in them? Well, there is this beautiful result of Garner and López-Franco that generalizes Eckmann-Hilton. If you have a duoid in such a category, then these two diagrams commute. So what do they say? They say that mu is determined by nu. Mu is nu precomposed with this canonical transformation sigma. Remember, sigma and tau are defined for all pairs of objects in the category. Okay, they're not part of the structure of the duoid. They're part of the structure of the category. So the first diagram tells you that mu is determined by nu. And the second one, well, once you know that nu is, and the second one tells you that it is determined in yet another way. So mu is determined by nu in two ways, by precomposing with sigma or by precomposing with tau. That's what this theorem says. In the setting of braided monoidal categories, sigma, remember, was the identity and tau was the braiding. So this is telling you that the two operations coincide, and this is telling you that the operation is commutative. So this is a generalization of Eckmann-Hilton to the setting of normal duoidal categories. So this is a nice result. And what we need for our work is to generalize this fact from objects, from duoids, to functors, to duoidal functors. So let's take a quick look at that notion. And I think I have 8 minutes, so we'll see how far we can go. At least I'm going to get you the results that are used in the application. I don't know if I'll be able to discuss the application. All right, if we're talking about functors between monoidal categories, there are two kinds of those, as we said at the beginning. We can consider monoidal functors or comonoidal functors. And that has to do with the direction of the arrow linking, perhaps I should have drawn something, linking the application of the functor to a product and the product of two applications of the functor to the two separate objects. So the arrow can go one way or the other, and then you have functors that are monoidal or comonoidal. When you go to duoidal categories, there are three kinds of functors, just as there were three kinds of objects: bimonoidal, duoidal, and coduoidal. And then the basic facts are that each of these kinds is closed under composition. If you compose two bimonoidal functors, you get another. And each kind preserves a corresponding class of objects. So in particular, duoidal functors preserve duoids. This can be seen as a special case of the previous item. Okay, so the important thing then is that there is a notion of duoidal functor and that they preserve duoids. So if you apply duoidal functor to a duoid, the object that you get can be endowed naturally with the structure of a duoid. Quickly, this is what the axiom for duoidal functors looks like. So you have two monoidal structures, keep referring to these things as monoidal structures. This is a monoidal structure for a functor, phi and gamma, okay, for diamond and for star, and they're linked by this axiom. This is the axiom for a duoidal functor. Here's our generalization of the result of Garner and López-Franco, or the first part of that. If you have a duoidal functor between normal duoidal categories, then it happens that these two diagrams, A and B, commute. So what this says is that the transformations phi and gamma intertwine sigma with f of sigma and tau with f of tau. So the duoidal axiom, which if you look here is a hexagon and it involves zeta, nothing about sigma and tau, but remember sigma and tau were specializations of zeta, implies that these two diagrams commute. If you apply this to the case when C is the trivial duoidal category with one object and one arrow, then sigma in the domain and tau in the domain, everything in the domain is trivial. So these rectangles become triangles, and these are the two triangles that Garner and López-Franco had. Because in that case, a duoidal functor boils down to a duoid. If your domain category is the trivial, the unit category, then such a duoidal functor is the same thing as a duoid in D. Okay, and that's how this result generalizes the one of Garner and López-Franco. Interestingly, there is also a converse. So if you have a functor between normal duoidal categories, and you know that axioms A and B hold, so you have two monoidal structures on the functor, but you don't know yet that it is duoidal. You don't know yet that the hexagon, the compatibility condition holds, but you know that A and B hold involving sigma and tau. You can prove that the hexagon holds. You need this. This is not so trivial. This is very interesting. I mean, in the end, it's the commutativity of a big diagram, but one needs to have this hypothesis. Okay, so this is a little more subtle than the previous implication. So we have this. If you specialize this all the way back to the very beginning of the talk, to the classical setting of Eckmann-Hilton, this is giving you the converse of Eckmann-Hilton, which is fairly trivial. It says that if you have one operation that is both commutative and associative, then you have this axiom. Okay, this is straightforward in that setting, but not in this setting of functors. And that is the key that we need for our application to Hochschild cohomology. Now, in 3 minutes, I cannot do justice to this. So what I'm going to do, so there's a few slides that I'll be very happy if any of you wants to read later. But let me just announce what the application is. So the Hochschild cohomology of an algebra with coefficients of a bimodule is something that can be defined. And it is defined as the cohomology of a certain complex, the standard Hochschild complex. And we want really to focus our attention on the complex. If the bimodule is of this kind, coming from an algebra B viewed as A bimodule by restriction, then you can define the cup product of cochains. So this object is the cochain complex is a ring. And it is not always commutative, but it is in certain cases. It is commutative when the algebra A is actually a bialgebra, and the algebra of coefficients is, say, the ground field as a trivial bimodule. Then the cup product is commutative up to homotopy, not on the nose, but up to homotopy. In particular, if you go to Hochschild cohomology, you get honest commutativity. Now, this result we extend to the setting of duoidal categories, but more importantly, we explain from the perspective of duoidal functors. How? Well, I would like to explain this result as follows. I would like to say that I look at the functor. Let me skip ahead. I look at the Hochschild functor here from the category of H bimodules to the category of cochain complexes. And I would like to say that that functor is duoidal. And then if I input a duoid here, since duoidal functors preserve duoids, I get another duoid in the target category E. But E is the category of cochain complexes. This is the standard category. It is symmetric monoidal. So here I have Eckmann-Hilton. So if I have a duoid in E, it has to be commutative. So can I do this? This is what I would like to do. This is the philosophy. Well, the difficulty is that this doesn't work because this functor is not duoidal on the nose, but it is duoidal up to homotopy. So this means that we have to be proving the commutativity of the duoidal axiom up to homotopy. One has to construct chain homotopies or cochain homotopies of cochain complexes. And this is not easy, but we are able to avoid that by proceeding as follows.
So Marcelo, as you noted, you're now in your question time.
I'm in my question time. So my last couple of sentences is this. what happens to this functor is that instead of attempting to prove that it is duoidal by directly looking at the hexagon that defines duoidal axioms, we look at axioms A and B, which we know are equivalent. And what happens is that axiom A holds when one uses for the monoidal structure of the functor a transformation known in algebraic topology as the Alexander-Whitney transformation. The other axiom B holds if one uses the dual or the reverse of Alexander-Whitney. So the axioms hold separately. Up to homotopy, it is a classical fact that the two transformations coincide. And for that reason, up to homotopy, A and B hold, and then the duoidal axiom holds. Okay, so that's perhaps summarized in this scheme here. This axiom that we wanted to prove, if you break it into two pieces, you can deal with each separately and then appeal to this classical fact that AW and AW tilde coincide to conclude that the two hold that simultaneously if you're working up to homotopy. Okay, so that's perhaps this is where I want to end. So that's all. All right, so I'm happy to chat if anybody wants to stay for a bit longer. So thanks everybody for holding.
Thank you, Marcelo.
Thank you, David.
So we do have 8 minutes for questions. So if you have a question, hit the react button and there's a raise hand feature on there and I'll call on you. So thank you for this. I wanted to note really quickly on the Garner duoid slide. I think that's there in what's it called? Theoretical computer science, they know that every monad, and I guess other people, every monad on set is is what they call applicative, is a Lax-monoidal functor. So I guess this is a case of that, I think, because deconvolution of times with composition is duoidal from set to set. So I think this is, yeah, I just a quick comment that I've seen this before. And also I think your bimodules slide where you had this kind of Hadamard product with the multiplication type thing, if that's a way to say it. I think that might also be true in any regular category.
You mean instead of working linearly over K modules?
Yeah, instead of looking, the previous, I think you were there. No, not that one.
This holds
Not that
over...
one. Oh, okay. But also the one with bimodules where you had to kind of.
Okay.
Yeah, this one.
This one?
I think of diamond as a Hadamard product, if that seem of matrices, and the star as a matrix multiplication, and that should hold for any regular category, I think. But I wanted to know if you had thought about that.
Thinking in terms of matrices, yes. Well, this is what I can say. This is not too far from the example of spans. If you linearize the case of spans and dualize, you end up with this, where R would be the category, the algebra of functions on the set X. So in that sense, this is again the example of spans. So I guess this connects with what you're saying.
Okay, cool. All right. Looks like Kevin has a question. Kevin, feel free to unmute.
Yeah, thanks a lot, Marcelo. Nice talk. I really like that duoid example of the monoid enriched stuff. I was wondering about your cosimplicial modules, funny monoidal structure that you and Batanen had developed.
Yes.
It's a little bit mysterious. I was wondering about maybe, do you know what happens if you apply Dold-Kahn and look at this structure on cochain complexes instead? Is that worse?
Yes, I think this is another way of understanding where this second monoidal structure comes from, as you're saying. So you use the equivalence. Since we're working with cosimplicial K modules, we have an equivalence with the Dold-Kahn correspondence with cochain complexes, and then this is the pullback under that equivalence of the usual structure on cochain complexes. So that's how you can understand it, but still, if you view it, so that wasn't too helpful for me, because what I really needed is to know that this operation was compatible with the other one, that they result in a duoidal category.
Mhm.
And that perspective, I didn't see how to use it for that purpose. Okay, so, and I think the definition is fairly natural, as is, so one can work with it, and that's what we do to check that this is duoidal. But yeah, Dolcan is there. So is that a
Yeah, that's helpful. So you're saying that actually you found it's hard to directly check for cochain complexes to check duoidality?
no? Because when you move to cochain complexes, you have one monoidal structure. So I'm not transferring this structure to
Oh
cochain
yeah,
complex.
okay. That doesn't transfer to the whatever you would call level-wise product, right?
You could transfer it, but I don't know what it would be. It would be
Right.
some kind of messy thing, right? So you will have the same problem on the other side.
Yeah,
So
that clarifies that. I was assuming it would transfer to the level-wise product, but sure, no reason for that. Yeah.
If you write this same thing for cochain complexes, you cannot turn this into another cochain complex. So
Yeah.
you cannot define a differential.
Right. Yeah. Thank you.
You're welcome.
Okay, we have a few more minutes for questions or comments. You gave an example. I mean, a duoid is a map out of one or whatever, a duoidal map out of one, which is a place where the two structures coincide.
Yes.
Do you know other cases of like a Lie group is, as you said, it's a monoid in, or a Lie monoid in topological, you didn't say this, but a monoid in topological spaces, and therefore I guess a duoid in your, you said every monoidal category has automatically both. I don't even know if that's a good case, but like maps out of topological spaces with times where the two products stop coinciding in the target category would send Lie groups to duoids or yes, to something. Just was wondering if you knew any cases of categories other than one where where the two structures coincide, but in maps out they diverge. I mean, and yeah, just as a kind of curiosity. Maybe Paul's question will be better, but if you have an answer.
Yeah, yes, I don't. So the example, you see, in the application, what we have is a little bit of the opposite, right? We are going, yes, I went over this too fast, but maybe you give me a chance to show this. So this is the category of bimodules, and this is an honest duoidal category. This is the category of cosimplicial modules, and this is normal. And this is the category of cochain complexes, and this one is braided monoidal. So here we have and this functor is duoidal. Both of these are duoidal, but the crux of the matter is on this functor that is only duoidal up to homotopy. So one has to post-compose with the projection to the category of cochain complexes up to homotopy. Okay? This is what I attempted to say very quickly before. So in regards to your comment now, this functor is going from a normal, so the unit objects coincide, but the monoidal operations are different, to one where everything coincides. But if you want to go the other way around, I don't know.
Yeah, the only one you mentioned was duoids, but yeah, it's interesting.
Yeah, other than the case of duoids, yeah.
Yeah.
But there may be natural
I'm sure there
examples.
are, yeah.
I just haven't
Paul,
fished it.
I want to let Paul have a quick word before we end. So Paul, feel free to unmute.
I wanted to make three fairly trivial comments. One is I love your flag.
Thank you.
Secondly, I was worried that you were inventing this very complicated algebraic structure with no applications in mind, but I see that you do have some applications. But I beg you to give some simple examples so that other people can follow what you're doing. My third trivial point is you run into the ambiguity of the prefix by. So we use by for, well, I made this mistake a long time ago. I invented the word bilimit before I knew about bicategories. And this is the example of the thing you're doing. So I propose that bi
Mhm.
meaning both sides, both a thing and a co-thing, that we use the prefix ambi instead.
Well, I like that, but the terminology bimonoids in the setting of braided monoidal categories is very established.
Well,
We didn't
so
impose
is
it.
bi for bi categories. And
Yes, I agree.
sometimes we have to change established things. That's my suggestion.
I appreciate it. Oh, let me just say this. We are coming from this algebraic side of things in which, and trying to generalize this fact about Hochschild cohomology of bialgebras. So again, the name that people use is bialgebras, not ambialgebras. So I wouldn't dare attempting to change that. So here's what I am referring to. This is the fact that we are able to generalize for Hochschild cohomology or of a bialgebra. So that's why I feel more or less constrained by that.
Great. Well, thank you, Paul, and thank you for Marcelo again for the great talk. And we'll stop the recording and we'll